Let's take a look at calculating the forces, or rather unknown forces, when it comes to rigid bodies. Let's say we have a random object. It could be a train, a plane, doesn't matter. For our example, it'll be a blob. If we know where the center of mass is, then we can say that the sum of all the forces acting on this object is equal to the mass of the object times the acceleration of its mass center. For the horizontal forces, we can write it like this, and for vertical forces, it'll be like this. In simple terms, all the forces in the x-axis added together would be equal to the mass of the object multiplied by the acceleration in the horizontal direction at the center of mass. The same goes for forces in the vertical direction. If an object goes through curvilinear translation, then instead of x and y components, we will use normal and tangential components. So if our blob is traveling along a curve, you probably remember that it will have a normal acceleration that's towards the center of the curve, while the tangential acceleration will be straight ahead. There is also something else we need to keep in mind. That is the moments affecting an object. Let's say we have moments or forces like these affecting our object. Then we can say the sum of moments about the center of mass is equal to the mass moment of inertia of the object times the angular acceleration. Today, however, we're going to focus on rigid bodies that go through just translational movement. In simple terms, the object is going to go in straight paths and not rotate or turn in circles. That means the angular acceleration of the object is 0. So we can write our moment equation like this. You will see when we do examples on how to use this to solve for unknowns. There is also another equation tied to this moment equation. That's when we calculate the moment about a point other than the center of mass. Instead of picking point G, which is our center of mass, let's say we pick a point right here. We will label it point P. To calculate the moment, we actually need to draw something called the kinetic diagram. To do so, we first pick the center of mass. Then we can draw a vector to show the mass times acceleration the object would experience due to all the forces or moments affecting it. If the blob is going through curvilinear motion, then we can draw two vectors that shows mass times the normal acceleration and mass times the tangential acceleration. So a kinetic diagram for our blob would look like this. We have the mass of the blob multiplied by the acceleration. We show the mass times acceleration that occurs due to the sum of all the external forces that's affecting the object. The direction of the acceleration is assumed. Now to write our moment equation, we use the free body diagram for the left side, and for the right side, we use the kinetic diagram. Remember that a moment is force times the perpendicular distance to the point where we're calculating the moment at. So for this example, our left side would look like this, and the right side would be like this. Notice how the vector we drew at the center of mass in the kinetic diagram is used to find the moment about point P. This might be a bit confusing right now, but after we go through examples, it'll become much clearer. The first example will be very easy without using any moment equations. In example number 2, we will calculate the moment about the center of mass. For the third example, we will calculate the moment about a point other than the center of mass, so we will look at how to use a kinetic diagram to solve the question. For the very last example, we will take a look at normal and tangential components. By the end, you should have a pretty good idea on how to solve the problems you will face. Let's take a look at this problem where we need to find the force in the links AB, CD, EF, and GH. First, let's draw a free body diagram of the canister. The canister is held up by two links, AB and CD. Each will carry a force. The only other force affecting the canister would be weight, which would be downwards. Now we can write an equation of motion for the vertical forces just for the canister. So we are ignoring the weight of the beam BD. We will pick up to be positive. So we have 2T, that's the two links holding the canister. Then we have the weight, so that's mass times the acceleration due to gravity, which is downwards, so that's negative. Then on the other side, we have the mass of the canister multiplied by the acceleration. The question says it's an acceleration of 2 meters per second squared upwards. We can solve for t, which gives us the force of each of the links AB and CD. Now let's consider the whole system. In other words, we're going to consider the beam that's on top. Let's draw another free body diagram. This time, the forces that's holding the beam is at an angle of 30 degrees. We also have to consider two weights, one of the beam and one of the canister. Let's write another equation of motion. So we have the y component of each force, so that's two forces, And then we have the weight of the canister and the weight of the beam. And that's equal to the mass of the whole system multiplied by the acceleration given to us. Solving gives us the forces in links EF and GH. Let's take a look at this question. We need to find the reactions at wheels A and B, and we will also need to find the acceleration of the cart. First, we will draw a free body diagram of the cart like this. So we have the 300 Newton force, the weight, and the normal reactions at wheels A and B. To figure out the acceleration, all we need to do is write an equation of motion for the horizontal forces, and we will pick left to be positive. So we have the x component of force P, and that's equal to the mass of the cart multiplied by the acceleration in the x direction. Since the cart only moves along the horizontal axis, there won't be any acceleration upwards. We can solve the equation, which gives us the acceleration. Finding the reactions at the wheels will require two equations since we have two unknowns, NA and NB. The first equation will be for vertical forces. So we have the two reactions at the wheels and the y component of force P, and from that we subtract the weight. On the other side, we have the mass of the cart multiplied by the acceleration, but again, the cart only moves in the horizontal direction, meaning it doesn't move up or down. So there is no acceleration in the vertical direction. Now we need another equation. For this, we will write a moment equation about the mass of center, point G. We will pick counterclockwise to be positive. Let's go through this equation, but first, imagine that we pin this cart at point G so it can freely rotate about the said point. If we apply the reactions at A like this, we see that the cart would turn clockwise. So then the moment is negative since we picked counterclockwise to be positive. Remember, moment is force times the perpendicular distance to the location where we are trying to find the moment at. So in this case, we have a distance of 0.3 meters from point A to point G. Then we have the reaction at B, and we see that if we apply that force, the cart would spin counterclockwise. So it'll be a positive moment, and the distance is 0.2 meters. Next, we have the 300 Newton force, which we can break into two components like this. If we look at the vertical force, which is 300 sine 30 degrees, we see that the cart would spin clockwise, so that would be a negative moment. The distance is from where the force is being applied to the center, which is 0.3 meters plus the 0.08 meters. For the horizontal force, we see that the cart would spin counterclockwise, so that'll be a positive moment. Since this is a horizontal force, we will consider the vertical distance to the mass of center, which means it's 0.4 meters minus 0.3 meters, giving us 0.1 meters. All of this is equal to 0 since the cart is not spinning and is only moving in the horizontal direction. We now have two equations with two unknowns. Solving them gives us the reactions at wheels A and B. Let's take a look at this example where we actually write a moment equation where it's not about the center of mass. So in this question, we need to show if it's possible for the front wheels of the car to lift up while the rear drive wheels are slipping. First, we will draw a free body diagram. We have the weight, the normal force at the rear wheels, but from the question, we know the front wheels are supposed to lift up, which means the normal force at the front wheels will be 0. Also, since the wheels are slipping while rolling, the frictional force will be pointing to the right. Now we need to draw a kinetic diagram. So what that means is, we need to use the center of mass given to us. Then we draw vectors that show the mass of the car times the acceleration it would go through due to all the forces affecting it. In this case, the car is only moving in the horizontal direction, so we'd have one vector pointing to the right. That would be 1500 times A. Using this, we can write a moment equation, but instead of writing it at the center of mass, we will write it at point B. Whenever we write a moment equation about a point, we can ignore the force being applied at that said point because it goes through the line of action. In simple terms, if we picked location A, then we ignore NA, and here since we picked location B, we ignore NB and the frictional force, which also goes through the line of action. So we will pick clockwise to be positive. You should also note that this moment equation is written with the free body diagram and the kinetic diagram. So on the left side, we have the mass times acceleration that causes a clockwise rotation, and the distance from the center of mass to point B is 1 meter. That's all the forces that will cause a moment for the free body diagram since NA is 0. Then on the other side, we look at the kinetic diagram. We see that the mass times acceleration at the center would cause a clockwise rotation, so that'll be 1500 A multiplied by the perpendicular distance to location B, which is 0.25 meters. We can solve for the acceleration. This is the acceleration at the center of mass of this car. Next, we can write our familiar equations of motion for horizontal and vertical forces. We have only the frictional force on the left side, and on the right side, we have mass times acceleration in the horizontal direction. Don't forget to plug in the acceleration we found. To find NB, we can write an equation for the vertical forces. So we have NB and the weight on the left side, and for the right side, remember, the car is only moving in the horizontal direction, so acceleration in the vertical direction is 0. We can solve to get the normal force at B. So the question asks us if it's possible for the driver to lift up the front wheels. Well, let's calculate the maximum friction that's possible. Friction is the normal force multiplied by the coefficient of friction. So this value we found tells us the maximum friction that the car can have with the coefficient of friction given to us. The value we found before tells us the required friction to lift the wheels up. In other words, when the wheels lift up, NA is 0, so we calculated the friction required to get NA to be 0. But with the coefficient of friction given to us, it's not possible to lift up the wheels since we can't get the maximum friction to equal the friction required. Let's take a look at one last question involving normal and tangential components. We need to find the largest initial angular acceleration before the box slips. In other words, how quickly can we rotate link DE before the box slips off? When we look at the diagram, we see that as the link DE is rotating, the box on top would be traveling along a curvilinear path. So let's draw our free body diagram, but instead of using our normal x and y coordinate system, we will use the normal and tangential coordinate system. We have the weight, the frictional force, and the normal force. We will also draw the acceleration vectors. So the normal acceleration would be towards the center of the curve, and the tangential acceleration would be straight ahead. Now we need to think about this problem. When theta equals 90 degrees, the angular velocity is 0. In other words, everything starts from rest. So remember how normal acceleration is angular velocity squared times r? Well, in this case, since everything starts from rest, normal acceleration at 90 degrees would be 0. To find the tangential acceleration, the equation is the angular acceleration multiplied by r. We don't know the angular acceleration since that's what we're trying to find, but we do know the distance from D to E, which is 1.5 meters. So we can write the tangential acceleration like this. If this is unfamiliar to you, please check the description for rigid bodies and rotation about a fixed axis. We can now write an equation of motion for the forces in the normal axis. We will pick down to be positive. So on the left side, we have the weight and the normal force. And on the right side, we have the mass of the crate multiplied by the normal acceleration, but that's 0. Let's solve for the normal force. Now an equation for the forces in the tangential axis. Keep in mind that friction is the coefficient of static friction multiplied by the normal force, which we just found. On the other side of the equation, we have the mass times the tangential acceleration. We can solve for the angular acceleration. That should cover the types of problems you will face in this chapter. I hope this video helped, and if it did, please consider sharing it with your friends and classmates. They too might find these videos helpful. Thanks so much for watching, and best of luck with your studies.